Here's something that will blow your mind. The universe is getting bigger right now. As you watch this video, every second, the space between galaxies is stretching, expanding, growing larger. And not just a little bit, the universe is expanding fast enough that distant galaxies are flying away from us at millions of miles per hour. But here's the really crazy part. Nobody knows exactly why. We know the universe is expanding. That's not up for debate. We can measure it. We can see it happening. We've been watching it for almost 100 years now. But the reason behind it, the force or mechanism that's pushing the universe apart, that's one of the biggest mysteries in all of science. And it gets weirder. The universe isn't just expanding, it's expanding faster and faster. The rate of expansion is accelerating. Something is pushing galaxies apart with more and more force as time goes on. We've given this mysterious force a name, dark energy, but we have no idea what it actually is. Today, we're going to explore one of the most profound discoveries in human history, that the universe is expanding. We'll look at how we discovered this, what it means, what's causing it, and where the universe is headed. We'll talk about the Big Bang, the mysterious dark energy, and what the far future of the cosmos might look like. This is a story that starts with a few observations of distant galaxies and ends with the ultimate fate of everything that exists. But before that, please make sure to like the video and subscribe my channel. So now let's begin at the beginning. Before we talk about why the universe is expanding, we need to understand what we used to think about the universe. Because for most of human history, everyone including scientists believed the universe was static, fixed, unchanging, eternal. This made intuitive sense. When you look up at the night sky, the stars look the same as they did last year, or 10 years ago, or 100 years ago. The constellations our ancestors saw thousands of years ago are the same ones we see today. Sure, planets move around, and the moon goes through phases, but the overall structure of the universe seemed permanent. Even Albert Einstein, probably the smartest physicist who ever lived, believed in a static universe. When he developed his general theory of relativity in 1915, he found something disturbing in his equations. His math suggested that the universe couldn't be static. It had to be either expanding or contracting. The equations just didn't allow for a stable, unchanging universe. Einstein didn't like this. He thought it was clearly wrong because everyone knew the universe was static. So he did something unusual. He added a fudge factor to his equations. He called it the cosmological constant. It was basically a force that would push against gravity just enough to keep the universe from collapsing while also preventing it from expanding. A cosmic balancing act. This cosmological constant had no physical basis. Einstein just added it because he needed the universe to be static to match what he thought reality was, and he wasn't alone in this belief. Pretty much every scientist at the time thought the universe was eternal and unchanging, but there were some problems with this idea that people were starting to notice. For one thing, if the universe is infinite in size, has existed forever, and is full of stars, then why is the night sky dark? This question is called Olber's paradox, named after the German astronomer who popularized it in the 1800s. Here's the logic. If there are infinite stars in every direction, then no matter where you look in the sky, your line of sight should eventually hit a star. The entire sky should be as bright as the surface of the sun, but it's not. The night sky is dark. Why? Some people proposed that dust between stars absorbs the light, but that doesn't really work because the dust would heat up and start glowing itself. Others suggested that maybe the universe isn't infinite after all, but that raised uncomfortable questions about what was beyond the edge. The real answer, as we now know, involves the universe expanding and having a finite age. Light from very distant objects hasn't had time to reach us yet, and light from objects that are far enough away is stretched by the expansion of the universe to wavelengths we can't see. But nobody knew this in the early 1900s. Then something happened that changed everything. In the 1920s, an American astronomer named Edwin Hubble, yes, the guy the Hubble Space Telescope is named after, made a series of observations that would completely revolutionize our understanding of the universe. But before we get to Hubble, we need to talk about something called redshift. This is the key to understanding how we know the universe is expanding. Imagine you're standing on a train platform and a train is approaching. As it gets closer, the train's whistle sounds high-pitched. Then, as the train passes you and starts moving away, the pitch drops lower. You've probably experienced this with ambulance sirens or cars driving past. The pitch changes depending on whether the source is moving toward you or away from you. This is called the Doppler effect, and it works with any kind of wave, including sound waves and light waves. With sound, when the source is moving toward you, the sound waves get compressed. More waves hit your ear per second, so the frequency is higher and the pitch sounds higher. When the source moves away, the waves get stretched out. Fewer waves hit your ear per second, so the frequency is lower and the pitch sounds lower. Light works the same way. If a light source is moving toward you, the light waves get compressed, shifting toward the blue end of the spectrum. We call this blue shift. If the light source is moving away from you, the waves get stretched out, shifting toward the red end of the spectrum. That's redshift. Now, every element produces light at very specific wavelengths. Hydrogen, helium, oxygen, iron, they all have unique fingerprints in the light they emit. Scientists can look at the light from a star or galaxy, see these fingerprints, and know exactly what elements are present. But here's what's interesting. When astronomers in the early 1900s started looking at distant galaxies, they noticed something strange. The light from these galaxies showed the right patterns for familiar elements, like hydrogen and helium, but all the lines were shifted toward the red end of the spectrum. The galaxies were red-shifted. This meant the galaxies were moving away from us. The farther away a galaxy was, the more red-shifted its light, and that meant the faster it was moving away from us. In 1929, Edwin Hubble published a landmark paper. He had been studying galaxies and measuring both their distances and their velocities, how fast they were moving away from us. What he found was remarkable. There was a direct relationship. The farther away a galaxy was, the faster it was receding. This relationship is now called Hubble's law. It's pretty simple. Velocity equals the Hubble constant times distance. In other words, if Galaxy A is twice as far away as Galaxy B, then Galaxy A is moving away from us twice as fast. This discovery was shocking. It meant that the universe wasn't static. Every galaxy was moving away from every other galaxy. The entire universe was expanding. Let me be clear about what this means. The galaxies themselves aren't moving through space. Space itself is expanding. It's like if you drew dots on a balloon and then inflated the balloon. The dots would move apart from each other, not because they're sliding across the balloon's surface, but because the surface itself is stretching. This is a crucial distinction. The galaxies aren't flying through space away from us. The space between galaxies is growing. New space is constantly being created between everything. When Hubble announced this discovery, it caused a crisis in physics. Einstein heard about it and reportedly said that adding the cosmological constant to his equations was the biggest blunder of my life. He realized he'd been right the first time his equations naturally predicted an expanding universe. He just didn't believe it and had tried to force them to show something different. But while Hubble's discovery showed that the universe is expanding, it didn't explain why. To understand that, we need to talk about the Big Bang. If the universe is expanding, if galaxies are all moving away from each other, then that raises an obvious question. If you run the movie backward, where were all the galaxies in the past? The answer: they were closer together. And if you go back far enough, they were all in the same place. Everything in the universe, all the matter, all the energy, all of space itself, was compressed into an incredibly tiny, incredibly dense, incredibly hot point. And then, about 13.8 billion years ago, that point exploded. Not exploded into space itself, exploded outward from that point. This is what we call the Big Bang. Now, I need to be clear about something. The Big Bang wasn't an explosion in the normal sense. It wasn't like a bomb going off in an empty room. Before the Big Bang, there was no room. There was no space. There wasn't even a before, because time itself began with the Big Bang. I know that's hard to wrap your head around. How can time have a beginning? What was there before time started? The honest answer is, we don't know, and the question might not even make sense. Asking what happened before the Big Bang might be like asking what's north of the North Pole. The question assumes something that doesn't exist. What we do know is that at the moment of the Big Bang, the universe started expanding, and it's been expanding ever since. In the first fraction of a second after the Big Bang, the universe was unimaginably hot and dense. We're talking temperatures of trillions of degrees. At these temperatures, matter as we know it couldn't exist. There were no atoms, no protons, no neutrons, just pure energy and fundamental particles. As the universe expanded, it cooled. About 1 second after the Big Bang, it was cool enough for protons and neutrons to form. After about 3 minutes, it was cool enough for these particles to stick together and form the nuclei of the simplest atoms, hydrogen and helium. But the universe was still too hot for electrons to stick to these nuclei and form complete atoms. The universe was an opaque fog of particles and radiation. Light couldn't travel very far before hitting something. Then, about 380,000 years after the Big Bang, the universe cooled enough for electrons to finally bond with nuclei and form neutral atoms. Suddenly, the universe became transparent. Light could travel freely. This is called recombination, and it's a crucial moment in cosmic history. The light from this moment is still traveling through the universe today. We can see it. It's called the cosmic microwave background, or CMB. It's a faint glow of radiation that comes from every direction in the sky. It's the afterglow of the Big Bang, cooled and redshifted by the expansion of the universe over billions of years. The CMB was accidentally discovered in 1964 by two scientists named Arno Penzias and Robert Wilson. They were testing a sensitive radio antenna and kept picking up a persistent noise from every direction. At first, they thought it was interference, maybe pigeon droppings on the antenna, but no matter what they did, the signal remained. It turns out they'd discovered the CMB, the most important piece of evidence for the Big Bang theory. They won the Nobel Prize for it. The CMB is remarkable. It shows us what the universe looked like 380,000 years after the Big Bang, and it's incredibly uniform. In every direction, the temperature of this radiation is almost exactly the same, about 2.7 degrees above absolute zero. This uniformity tells us that the early universe was almost perfectly smooth and homogeneous. But not perfectly smooth. There are tiny variations in temperature, only about 0.001, that represent slight differences in density in the early universe. And these tiny variations are crucial. They're the seeds that eventually grew into galaxies, stars, planets, and us. Over billions of years, gravity amplified these tiny density differences. Regions that were slightly denser attracted more matter. They became even denser. Eventually, they collapsed into the first stars and galaxies. So the Big Bang explains why the universe is expanding. It's expanding because it started in an incredibly hot, dense state and has been spreading out ever since. The expansion we see today is basically leftover momentum from that initial explosion billions of years ago, or at least that's what scientists thought for a long time. But then, in the late 1990s, astronomers discovered something that changed everything again. Here's what scientists expected. The universe is expanding because of the Big Bang, but that expansion should be slowing down over time. Why? Gravity. Every piece of matter in the universe attracts every other piece through gravity. This means the expansion should be working against gravity. It's like throwing a ball up in the air. The ball moves upward because you gave it energy, but gravity pulls it back down, slowing it until it eventually stops and falls. Similarly, the universe should be expanding, but gravity should be pulling everything back together, slowing the expansion. Scientists thought the key question was, is there enough matter in the universe for gravity to eventually stop the expansion and cause everything to collapse back together in a big crunch? Or is there not enough matter, meaning the universe will expand forever, just at an ever-slowing rate? To answer this question, two teams of astronomers in the late 1990s set out to measure exactly how much the expansion was slowing down. They looked at distant supernovas, exploding stars that are so bright they can be seen across billions of light years. A specific type called Type Ia supernovas are really useful because they always explode with roughly the same brightness. This makes them great standard candles for measuring cosmic distances. By comparing how bright they appear to how bright they should be, you can figure out how far away they are. And by measuring their redshift, you can figure out how fast they're moving away. Both teams expected to find that the expansion was slowing down. They just wanted to measure by how much. But what they found was completely unexpected. The expansion wasn't slowing down, it was speeding up. Distant galaxies weren't just moving away from us. They were accelerating, moving away faster and faster over time. This was announced in 1998, and it was so shocking that at first, many scientists didn't believe it. There must be some mistake in the measurements, they thought, but as more data came in, the result held up. The universe really is accelerating. In 2011, the leaders of both research teams, Saul Perlmutter, Brian Schmidt, and Adam Rees, won the Nobel Prize for this discovery. Think about how weird this is. Imagine throwing a ball up in the air, and instead of slowing down as gravity pulls on it, the ball speeds up. It goes faster and faster into the sky until it disappears. That's not how gravity works. Yet that's apparently what the universe is doing. Something is pushing the universe apart, and that something is getting stronger over time, or at least overcoming gravity more and more. We don't know what this force is. We've given it a name, dark energy, but that name is basically an admission of ignorance. We're saying there's some kind of energy out there making things accelerate, and we have no idea what it is. The discovery of accelerating expansion is probably the biggest mystery in modern physics. It tells us that there's something fundamental about the universe that we don't understand, some force or property of space that acts opposite to gravity, pushing things apart instead of pulling them together. And here's the kicker. Dark energy isn't a small thing. When we calculate how much dark energy there must be to cause the acceleration we observe, we find that it makes up about 68 of all the energy in the universe. regular matter atoms, stars, planets. You, me makes up only about 5. Another 27 is dark matter, which is another mystery we don't fully understand. So we live in a universe where 95 of the content is stuff we can't see, don't understand, and have no idea what it really is. That's humbling. So what is this dark energy that's pushing the universe apart? The honest answer is, we don't know, but we have several ideas, and each one is fascinating in its own way. The first possibility is that dark energy is the cosmological constant that Einstein invented and then abandoned. Remember, Einstein added this to his equations to keep the universe static. It was a kind of energy that fills empty space, creating a repulsive force that pushes against gravity. When Einstein heard about the expanding universe, he threw out the cosmological constant, thinking it was wrong, but maybe he was right in a different way. Maybe empty space really does have energy. Maybe the vacuum of space isn't truly empty, but has a baseline energy level that causes expansion. This idea is called vacuum energy. In quantum mechanics, even empty space isn't truly empty. Virtual particles constantly pop into existence and disappear. The uncertainty principle of quantum mechanics means that space is actually seething with activity at the quantum level. This activity has energy, and maybe that energy is what we're seeing as dark energy. The problem is, when physicists try to calculate how much vacuum energy there should be based on quantum mechanics, they get an answer that's wrong by a factor of about 10 to the power of 120. That's not a typo. Their calculation gives an answer that's 1 followed by 120 zeros times larger than what we observe. This is sometimes called the worst prediction in the history of physics. So either quantum mechanics is dramatically wrong about something, or there's some unknown mechanism that cancels out almost all of the vacuum energy, leaving just a tiny bit, exactly the amount we need to explain dark energy. We don't know which. Another possibility is that dark energy isn't constant. Maybe it changes over time. Some theories propose what's called quintessence, a dynamic form of dark energy that can vary in strength. Unlike Einstein's cosmological constant, which is the same everywhere and always, quintessence could be stronger or weaker in different regions of space or at different times. If quintessence is real, the fate of the universe could be very different from what we'd expect with a constant dark energy. The expansion might speed up for a while, then slow down, or change in other ways. We'd need to measure dark energy very precisely over time to detect this. A third possibility is that we don't fully understand gravity. Einstein's general relativity works perfectly well for everything we've tested it on orbits of planets, bending of light around the sun, gravitational waves from black holes. But maybe at the largest scales, billions of light years, gravity works slightly differently than we think. Some scientists have proposed modified theories of gravity that would naturally produce accelerating expansion without needing dark energy. These theories are controversial though, because they require changing Einstein's relativity, which has been so successful at explaining everything else. There's also the possibility that dark energy is related to extra dimensions. Some theories in physics suggest that our universe might have more than the 3 spatial dimensions we experience. These extra dimensions might be curled up so small we can't see them, or they might be accessible only to gravity. Maybe dark energy is related to how these extra dimensions behave. String theory, which attempts to unify quantum mechanics and general relativity, often predicts extra dimensions. Maybe understanding how these dimensions work would help us understand dark energy. Here's another wild idea. Maybe dark energy is a sign that we live in a multiverse. Some versions of inflation theory, which we'll talk about in a bit, suggest that our universe is just one bubble in an eternally inflating space. Other universes might exist beyond our cosmic horizon. Maybe dark energy is related to the interaction between these bubble universes, or to the properties of the larger space that contains them. Or maybe dark energy is something we haven't even thought of yet. Something so different from our current understanding of physics that we don't have the framework to conceive of it. History shows that revolutionary discoveries often come from completely unexpected directions. What we do know is that dark energy seems to behave consistently with Einstein's cosmological constant as far as we can measure. It doesn't seem to change over time or vary from place to place. It has a constant density even as the universe expands. This is weird when you think about it. Normal matter gets less dense as the universe expands. If you have a certain amount of stuff in a box and you make the box bigger, the density goes down, but dark energy doesn't work that way. As space expands, more dark energy appears to fill that space, keeping the density constant. It's as if dark energy is a property of space itself, not something that exists in space. This property is what makes dark energy so powerful. As the universe expands, there's more space, which means more dark energy, which means more pushing force, which means faster expansion, which creates even more space. It's a runaway process. Scientists are working hard to understand dark energy better. We're building new telescopes and surveys to measure the expansion rate of the universe more precisely. We're looking for any signs that dark energy might be changing or behaving differently than expected. We're testing alternative theories of gravity, but right now, after more than 25 years since its discovery, dark energy remains one of the deepest mysteries in science. We know it's there because we can see its effects, we can measure it, but we don't know what it is. Before we talk about the future of the universe, there's one more piece of this story we need to cover: cosmic inflation. This is a theory about something that happened in the first tiny fraction of a second after the Big Bang. The Big Bang theory, as originally conceived, had some problems. One was called the horizon problem. The cosmic microwave background looks almost perfectly uniform in all directions. The temperature is the same to within 0.01 no matter where you look, but according to the standard Big Bang model, different parts of the universe should never have been in contact with each other. They're too far apart. Light hasn't had enough time to travel between them. So how did they all end up at exactly the same temperature? It's like finding that your house and a house in China are at exactly the same temperature, even though the thermostats have never communicated. There's also the flatness problem. The universe appears to be almost perfectly flat in its geometry. Not flat like a pancake, but flat in the sense that the angles of a triangle add up to exactly 180 degrees on cosmic scales. This flatness requires the density of the universe to be very precisely tuned. If it was even slightly different in the early universe, the universe would either have collapsed quickly or expanded so fast that galaxies couldn't form. Why is the density so precisely right? In 1980, a physicist named Alan Guth proposed a solution: cosmic inflation. His idea was that in the first tiny fraction of a second after the Big Bang, we're talking 10 to the power of minus 36 seconds, which is 0.1 seconds, the universe underwent an incredibly rapid expansion. During this inflationary period, the universe doubled in size many times in rapid succession. Some versions of the theory suggest it doubled at least 60 times, meaning the universe grew by a factor of at least 2 to the power of 60, or about a billion, all in less time than it takes light to cross the nucleus of an atom. This rapid inflation would solve both problems. It would explain uniformity because the parts of the universe we can see were all in close contact before inflation, allowing them to reach the same temperature. Then, inflation stretched them apart to vast distances. It would also explain flatness, because inflation stretches space so much that any curvature gets smoothed out. Imagine inflating a balloon to the size of the Earth. The surface would look perfectly flat from the perspective of an ant standing on it. But what caused inflation? This is where it connects to dark energy. The idea is that in the early universe, there was a field called the inflaton field that had very high energy. This energy was similar to dark energy in that it caused space to expand rapidly. Eventually, the inflaton field decayed. Its energy got converted into matter and radiation, ending the inflationary period and starting the regular Big Bang expansion we're more familiar with. This conversion of energy to matter is sometimes called reheating. So inflation was like a brief period where the universe was dominated by something like dark energy, causing exponential expansion. Then, that energy source shut off, and gravity took over, slowing the expansion. And now, billions of years later, dark energy has become dominant again, and the expansion is accelerating once more. This raises an interesting question. Is the dark energy we see today related to the inflaton field from cosmic inflation? Are they the same thing, but at different energy levels? Or are they completely different phenomena that just happen to have similar effects? We don't know. Inflation theory makes specific predictions about patterns we should see in the cosmic microwave background, and amazingly, when we've looked for these patterns, we've found them. This is strong evidence that something like inflation really happened, but we still don't know what the inflaton field was, what caused it to exist, or why it decayed. Inflation solves some problems but creates new questions. There's also the possibility that inflation never stopped. Some versions of inflation theory suggest that while inflation ended in our region of space, it continues eternally in other regions. This leads to the concept of eternal inflation and the multiverse, an infinite number of bubble universes, each with potentially different properties, constantly being created in an eternally inflating background space. In this picture, our universe is just one bubble among infinite bubbles. Our Big Bang was just the moment when inflation ended in our particular region, and dark energy might be a leftover remnant of the inflaton field, a small echo of the force that created our universe. These ideas are highly speculative and controversial, but they show how trying to understand the expansion of the universe leads to profound questions about the nature of reality itself. So the universe is expanding, and that expansion is accelerating. What does this mean for the future? Where is all of this heading? If dark energy remains constant, if it doesn't change in strength, then the future is pretty clear, and honestly, it's kind of depressing. As the universe continues to expand and accelerate, galaxies that are currently close to us will move farther away, but galaxies that are really far away, billions of light years distant, will eventually move away from us faster than the speed of light. Wait, faster than light? I thought nothing could move faster than light. That's true for motion through space, but there's no limit on how fast space itself can expand. As space expands between us and a distant galaxy, that galaxy can end up receding from us faster than light, even though it's not actually moving through space that fast. It's like being on a conveyor belt that's moving faster than you can run. You can run forward, but you still move backward relative to someone standing still. Once a galaxy crosses this threshold, called the cosmic event horizon, we'll never be able to see it or communicate with it again. The light it emits will never reach us because space is expanding too fast between us. Over billions of years, more and more galaxies will cross this horizon. The observable universe will shrink. The night sky will become darker and emptier. Eventually, in tens of billions of years, the only galaxies we'll be able to see will be the ones in our local group, the Milky Way, Andromeda, and a few dozen smaller galaxies that are gravitationally bound to each other. Everything else will have been carried away by the expansion. By this time, most stars will have burned out. The universe will be darker, colder, and emptier. Our local group of galaxies will have merged into one giant elliptical galaxy, and that galaxy will be alone in an expanding void. As more time passes, hundreds of billions or trillions of years, even the remaining stars will burn out. Black holes will be the main objects left, and in this dark, cold universe, the expansion will continue, accelerating everything apart. Eventually, even black holes will evaporate through a process called Hawking radiation. This takes an unimaginably long time, 10 to the power of 100 years for the largest black holes. But in the end, even they'll be gone. The final state of the universe would be a thin soup of particles spreading apart forever, getting more and more dilute, approaching absolute zero in temperature. This is called the heat death of the universe. It's the maximum entropy state total disorder. No structure, no complexity, no life. It's a bleak picture, but it's based on the assumption that dark energy stays constant. If dark energy changes, the story could be different. If dark energy gets weaker over time, the expansion might slow down again, and gravity could eventually win. The universe might stop expanding and start contracting, eventually collapsing in a big crunch, the opposite of the Big Bang. Everything would come back together in a hot, dense state, possibly creating conditions for a new Big Bang, a cyclic universe. On the other hand, if dark energy gets stronger over time, things could get really weird. In this scenario, called the Big Rip, the accelerating expansion would eventually become so powerful that it would overcome not just the gravity holding galaxies together, but also the gravity holding solar systems together, planets together, molecules together, and even atoms together. Billions of years from now, galaxies would be torn apart. Then, closer to the end, solar systems would be ripped apart, planets would be shredded, then atoms themselves would be split apart. The entire universe would be torn to pieces by the expansion. This scenario is probably unlikely based on what we currently observe, but we can't rule it out completely until we understand dark energy better. There's also something called the Big Freeze, which is similar to heat death, but focuses more on the cooling aspect. Eventually, the universe becomes too cold for any processes to occur. Everything grinds to a halt. Whatever the exact details, if the universe continues expanding, the distant future looks pretty empty and dark. Of course, we're talking about timescales so long, they're almost meaningless. Trillions upon trillions of years. The universe is only 13.8 billion years old now. The heat death wouldn't happen for at least 10 to the power of 100 years. By comparison, the Earth will be uninhabitable in about 1 billion years when the sun gets too hot. The sun will die in about 5 billion years. All the stars in the universe will burn out in about 100 trillion years. That's still nothing compared to the timescale for heat death, but these distant futures are all speculation. We don't know what dark energy really is, or whether it will remain constant. We don't know if there are new physics we haven't discovered yet that might change things. We don't even know if our universe is the only one. What we do know is that right now, at this moment in cosmic history, we live in a universe that's expanding, accelerating, full of stars and galaxies and life, and that's pretty amazing. So why is the universe expanding? Because it started in an incredibly hot, dense state 13.8 billion years ago and has been spreading out ever since. That's the Big Bang, and it's the foundation of everything we observe. But why is it accelerating? That's the trillion-dollar question. We know there's something called dark energy pushing things apart, but we don't know what it is. It might be energy inherent to space itself. It might be a dynamic field that changes over time. It might be related to quantum mechanics, or extra dimensions, or something we haven't even imagined yet. What's remarkable is how much we've learned in just the last 100 years. In 1920, we didn't even know there were other galaxies. We thought the Milky Way was the entire universe. Now we know there are hundreds of billions of galaxies, each with billions of stars, all rushing away from each other in an accelerating expansion. We've measured the age of the universe 13.8 billion years. We've mapped the cosmic microwave background and seen the universe as it was just 380,000 years after the Big Bang. We've discovered that the universe is mostly made of things we can't see: dark matter and dark energy. We've traced the history of cosmic expansion from the first fraction of a second to the present day, and yet we still don't understand the most basic question: why is all of this happening? What is the force driving the expansion? Scientists are working on it. New telescopes and surveys are measuring the expansion more precisely. Particle physicists are searching for clues about dark energy in their experiments. Theorists are developing new models and ideas. Maybe in your lifetime, we'll figure it out. Maybe some brilliant scientist will have an insight that makes it all clear. Or maybe this mystery will take centuries to solve, requiring physics so advanced we can't even conceive of it yet. Either way, the fact that the universe is expanding, that space itself is growing, that we live in a dynamic, changing cosmos rather than a static, eternal void, that's one of the most profound discoveries in human history. Every second, the universe gets a little bit bigger, galaxies drift a little bit farther apart, and somewhere in all that expanding space, we exist, asking questions, trying to understand, marveling at the mystery of it all. That's the reason the universe is expanding, or at least, that's as close to an answer as we have right now.